Hi, I'm Jun Nakajima from Intel. Today, I'm going to talk about implementation options of KVM-based Type 1 or 1.5 hypervisor. Before that, I'd like to appreciate Chanshao and Anthony for their effort and contribution to this project. They implemented POCs and also measured a lot of data for this project. Anyway, thank you very much, uh, Jamson and Anthony. So as usual, now that danger, I'm starting from the motivation and show some implementation options and then POC performance data and followed by our conclusion next step. Okay. I presented this at the last KVM forum, but at that time I pointed out the security risk of guests on Linux KVM. Basically, KVM piggybacks or depend on the Linux, the host, and Linux is, as you know, needs to run various operating system workloads, and it's much larger than KVM itself or hypervisor. So it has more attack surfaces and making the guest more exposed. Also, user space PMM like a QEMU has full access to the guest memory, also guest CPU state. And then the kernel has full access to any guest memory or CPU state. So that's a kind of security risk of existing uh, Linux KVM implementation. Okay. So the motivation of a Type 1 hypervisor, uh, this is not the new, for example, if you look at Zen, it's kind of a 1.5, and then also Hyper-V and then other hypervisor has a similar architecture. The benefits of the Type 1 or Type 1 point hypervisor is it separates the hypervisor from uh, Linux, which handles more complex operations and, for example, I/O with using various device drivers from various parties and process management, user process handling. Whereas the hypervisor will be responsible for isolation. And then also, if trusted, hypervisor can create secure environment like trusted execution environment or trusted VMM on top of a hypervisor. Now take a look at how we can uh, how we can convert KVM to type 1.5. Okay. So we take a standard Linux plus KVM system and then insert hypervisor as L0. Now the KVM becomes L1 and then the existing VMs become like a nested, so L2. Okay. But we still want to keep IO path-through. Um, so the hypervisor itself basically doesn't have any device driver, IO device driver. Okay. And then we call DOM0 like a Zen guys did. Essentially, this is very similar to the Zen architecture. The difference would be the as a DOM0 it uses basically unmodified Linux. Okay, but there are more differences I'll talk about. And in terms of implementation, we have two extremes. One extreme is as hyper, I'm talking about the hypervisor implementation. One extreme is to use minimally configured Linux, okay, plus KVM. And since it's a Linux, although it doesn't have a IO device driver, it's basically an operating system. It has a scheduler, memory management, and so forth. Okay, and then it boots first and separately from the DOM0. Okay, as a Linux, it can run user processes and it can run user level VMMs for DOM0. We cannot use a QEMU per se, mainly because it doesn't need to. It doesn't need to, not use a QEMU because IO virtualization is not really required there. Okay. For other VMs, we probably need to use QEMU. This is one implementation, and the other side is they say the lightweight hypervisor. The It's simply just a deprivileged Linux for isolation, and it's just reactive. So as long as the host Linux behaves, guest Linux behaves well, it doesn't generate the VM exit. Okay, and this can be loaded by Linux at the early boot time, as long as the Linux was the healthy at that time. Okay, and then common thing is again IO pass-through. So let's talk about pros and cons for each implementation option. Okay, one is Linux KVM hypervisor. So again, the hypervisor is minimally configured Linux plus KVM. Okay, so it has a user level as well. It's user support like the DOM, the user level VMM, and then the QEMU. The benefits as a hypervisor, uh, you can run unmodified guest on L1 here. And since the hypervisor is a Linux KVM, you can benefit from a Linux KVM also, continue to benefit, right? But there are some disadvantage of this approach. First of all, I'll talk about it later, but the higher latency to DOM0 because of scheduling, double scheduling, and then VM exit. And it's still big, so it may have issue as a TCP. Well, we may be able to handle that. Okay. And then BART-IO for the guest. As long as you run the guest within a DOM0, it switches just a Linux, a typical Linux system. But this guy, this L1 is outside DOM0, and there are some issue with handling BART-IO for this for these VMs. Also, power management is essentially who should manage the power for the CPUs and then the platform. Okay. So I'll talk about some scheduling and then power management issues here. As hypervisor with Linux, it needs to own the VM scheduling. Okay. To that end, we need to intercept, halt, emulate in DOM0. But this causes inefficiency especially for the client because of two-level scheduling. So now we have scheduling at the two levels in the hypervisor Linux and then also within the DOM0 Linux kernel. And because of those we see unexpected latency in VMs, especially in a DOM0. Now, other issue is how we gonna create the VMs. Um, we need to invoke the QEMU process here to create the L1 VMM. L1 VM. But from a user point of view, this user process is available. You cannot really access to hypervisor level of a user space. Okay, so we need have some communication, secure communication to from a user level in DOM0 to hypervisor or the QEMU or some process on the hypervisor side. Virtualization is also a problem because from the QEMU process point of view, he doesn't have a device driver available in the hypervisor. Only memory file system will be available. So QEMU can in the hypervisor run VM without Virtualization. So it's limited. There are probably ways to allow that QEMU to access the real I/O devices, but we don't know how at this point. Okay, probably we need something like a Zen or a Hyper-V kind of a solution here. So switch to the lightweight hypervisor. Pros is, like I said, code path. If you look at the code path of this DOMs, the code path is basically almost probably identical to the bare metal, same code to the bare metal Linux KVM, and that's a low overhead and then a low latency, and then it's small TCB. Okay. The disadvantage is if you want to run the L1 VM, for example, in enclave or secure environment for purpose, then we have kind of similar problem. Basically, this lightweight hypervisor doesn't have any device drivers. So, and then also no user process available. So it's not so easy to support virtual devices in the L1 VMs. You can run the unmodified guest, but that's the case. In that case, the VMs will be run as L2 as a KVM guest, which is L1 nested. Okay, so there may be some performance concern with that. There are some optimization when running a KVM guest on top of lightweight hypervisor. So one is so-called optimized nesting. I'll talk about more details on the next page. But we can pass through most of the fields of shadow VMCS. And also we can convert the shadow VMCS to real VMCS very quickly, just flipping one bit. Anyway, I'll talk about more detail next page. The other technique we have is we can have the KVM, the first level entry point inside the lightweight hypervisor, then handle the VMXs immediately inside L0 hypervisor and quickly go back. For a more complex handling, we need to go back to KVM. So in that case, we need to enter the KVM or the DOM0 for that part. But still, it's uh, faster as long as we can handle within the L0 hypervisor. In that case, the L2 VM looks like kind of a L1 VM. Okay. So now I'll talk about more details on nested virtualization. For nested virtualization in a KVM, we use the so-called VMCS shadowing. And the benefits of VM shadowing is it doesn't need to cause the VM exit upon VM read or VM write in L1 VMM. So if the hypervisor allow the the guest VMM to directly access the VMCS, then it doesn't need to generate the VM exit. It just access the VMCS. The hypervisor can set the bitmap for the VMCS fields, read and write, the separate bitmaps for read and write operation. So as long as they are not in the bitmap, then uh, the L1 VMM can just simply do the operation VM read or VM write operation without causing VM exit to the L0 VMM. But sometimes it needs to generate the L0 VMM needs to intercept, and even still we use the VMCS shadowing. Certain writes or read to the VMCS field causes a VM exit. Also, the biggest problem with the VMCS shadowing is this shadow VMCS itself cannot be used for VM entry. So when we go back to the L2 VM, we need to copy or sync some the VMCS field so that we can make a real VMCS for the VM entry back to the L2 VM. Now, the optimization we have doesn't require copy or sync because the VMCS shadow or shadow VMCS is it's identical to the real VMCS. We still need to intercept the some limited the VMCS field by the L1 VMM for security purposes, but the contents are basically same, so we can just flip the bit. Now we took. Now let's talk about the POC. So we extended VBH to create the lightweight hypervisor POC. The original VBH is virtualization-based hardening. It simply deprivileged the Linux kernel to harden the kernel using hardware-based virtualization features. We pass through all I/O and also epic. And in the POC from the VBH, beyond the VBH, we added simple nesting support. This only works for the L1 VMM, like a bare metal VM, where the GPA is identical to HPA. Like I showed, we implemented optimized VMCS sharding and also virtual EPT to make sure isolation. Also added a feature to run a simple L1 VM in trusted environment. We can run Opti OS. Please look at the pointer below. And we are working on virtual MMU, IOMMU support. Okay, now let's take a look at the performance data. What kind of performance data we have by comparing the VM L1 or L2 VM performance on KVM-based hypervisor versus the lightweight hypervisor. So we are comparing the VM L2 VMs on top of Linux KVM hypervisor versus lightweight hypervisor. So the first performance measurement is the comparison of L2 VMs. Okay, so this is kind of result, and this one shows the improvements from flipping, the shadow VMCS indicator, that the 1 bit. Okay, so if you look at the VM exit cost, initially KVM had this much, but now it's more than like a 1/10. Okay, less than 1/10. So you see a consistent, you know, result in terms of the VM exit uh, latency reduction, like about 10x or more. Okay. Also, at the time of a VM entry, uh, because of a fast switching, you also see like almost a 10x improvement, or more than 10x improvement. So we have a very good L2 performance, okay, compared with the KVM L2. If we compare KVM L1, okay, versus that L2 on a lightweight hypervisor, okay, so this is a result. Okay, result is it's almost same. We have some regression in I/O area at this point, but this is kind of first implementation, so we don't have any optimization for I/O at this point. But so the performance looks good, and then we don't have the another optimization like a KVM faster entry point handling. Okay, so today the L2 VMs on lightweight hypervisor runs purely in nested way. So from POCs, we found a couple of things. So we also have a POC for the Linux KVM hypervisor. It actually has structural impact. Okay, the structural impact in the sense of a resource management. Okay, scheduling, like I said, the double scheduling, and then also power management. The Linux as a hypervisor needs to have the power management. Although hypervisor doesn't have any I/O devices, it needs to handle. Still needs to handle the VM management. But from a user point of view, I mean, the user of L0, DOM0 uh, user level, it doesn't allow to manage the VM directly, because the QEMU on the DOM0 just handles the VMs on the DOM0. Okay. Versatile implementation will be a bit tricky. We need similar solution like Zen or Hyper-V provides, like ZenBus and the back end and the front end solution. The bigger challenge is to kind of redo all the performance or validation work if we switch to this one, because you have a different resource management structure, right? Large difference here. In terms of performance or tuning, um, you cannot really get same results as a bare metal. Once you have this hypervisor, this architecture, you need to redo the optimization and tuning. On the lightweight hypervisor side, we had some concern with nesting, and at this point, the performance of L2 on a lightweight hypervisor and then the KVM L1 is almost the same except uh, IO. IO is about 90% of L1 KVM at this point. So we still need more optimization for IO. Here's our conclusion. The lightweight or reactive hypervisor approach is more suitable for the existing Linux KVM when making it more secure, i.e. Type 1 or 1.5 BMM, because we can maintain the same code path as the bare metal Linux KVM, including scheduling and power management, so forth. It also provides low latency and overhead. In addition, the VBH-based hypervisor can harden the DOM 0 kernel and guest kernel as well. KVM Guests also run with minimal overhead, even though they run in an L2 environment. We also found advantage when implementing trusted execution environment because of a small TCV. So this is the next step. So we want to finish the VBH-based POC, especially complete IOMMU virtualization and optimize KVM guests more, especially in buffer IO areas, especially IO write operations. We also add first level KVM entry point in VBH, and then after that we share the source code. With that, this is end of my presentation. Thank you.